Welcome back, everyone. Today we will be talking about exceptions. So far in this course, we have mostly focused on writing code that works when everything goes according to our plan. So we create objects, we call functions, we return values, we calculate stuff, and life is good. But real software doesn't live in a perfect world. Your memory might run out, files disappear, network connections fail, users type things that they really shouldn't. Hardware sometimes behave unexpectedly, and even a neutrino might hit your computer and flip a bit, and your program might go out of scope. That's a real incident. You might want to check that out. So the interesting question isn't whether the program goes through an error or not. They always do. The programs always might break. So the real question is, what should our program do when something goes wrong? If we ignore the problem, we may produce incorrect results. If we stop the program immediately, we might lose data. If we write error checking everywhere, our code can quite become difficult to read and maintain. So, before we look at the C++ syntax on how to handle these errors and how to handle these unwanted situations, let's first understand why exceptions exist. We will use a simple example for that. Imagine we are writing a software for an automated smoothie shop. A customer orders an apple smoothie. Our software has a simple workflow, and in that workflow, it first checks whether the fruit is fresh or not, and then if the fruit is good, it mixes the smoothie. Finally, it serves the smoothie to the customer. Seems straightforward. But now let's imagine one of the apple has gone bad. Nobody wants a rotten smoothie, right? So we decide that before anything else happens, we will inspect the fruit carefully. If the fruit isn't safe, we want the whole process to stop before the blender even starts. That sounds like a simple problem. In fact, many beginners would immediately think, I'll just return true if everything is okay and false if something is wrong. And honestly, that's a perfectly reasonable first idea. Even I did that. So let's see how that looks. Here's our first layer. We have a function whose job is only checking the fruit. Suppose it inspects an apple. If the apple looks fresh, the function returns true. If it detects a rotten apple, it returns false. Nothing fancy here. Returning a Boolean value is probably the first error handling technique most programmers learn. The function communicates one simple fact. Is everything okay? Or something went wrong? At the first glance, this seems completely efficient. After all, whoever calls this function can simply look at the return value and decide what to do next. So far, everything looks safe. Now, let's move one level higher in our program. Now we are inside the function that prepares the smoothie. This function doesn't inspect the fruit itself. Instead, it asks the previous function to do that. It might look something like this in plain English. Let me translate that for you. So, at first, it asks, check the fruit. Then it stores the answer inside fruit is good. Then it continues. If the fruit is fresh, then fruit is good becomes true. Otherwise, it becomes false. Now notice something important here. The information hasn't disappeared. The bad fruit has been detected. But the result is sitting right there inside a variable, and at this point, everything still depends on what the programmer does next. Will they actually check that variable, or will they accidentally ignore it? So let's see the final layer. Now we are back at the highest level of the application. This is where everything comes together. The customer presses the button, the program starts making the smoothie, eventually it reaches the point where it serves the drink. From the user's perspective, this is all they ever see. They don't care about helper functions or hardware sensors. They only care whether the correct smoothie comes out or not. And that's exactly why mistakes at lower levels become dangerous. If the earlier warning somehow gets ignored, this function has no idea that something already has gone wrong. Let's see what actually happens when we run the program. Okay, so the program happily serves the smoothie, but we already know that the apple was rotten. How did that happen? The fruit checking function actually worked. It correctly detected the problem. It even returned false. Somewhere between detecting the problem and serving the smoothie, that information got lost. This kind of bug is surprisingly common, and the computer didn't misunderstand us or anything like that. The program did exactly what we told it to do. The problem is that somewhere along the way, a programmer forgot to react to the warning. And that's much harder to notice rather than a compiler error. The code still compiles, the program still runs, it just quietly does the wrong thing. Let's follow the journey of that false value. Layer 3 checks the fruit, it detects the rotten apple, it returns false. Layer 2 receives that value, it stores in fruit is good, then it simply returns the same value to the next layer. Still okay. Then layer 1 calls the smoothie function, and here's the mistake. It completely ignores the returned value. It never asks whether the operation succeeded or not. It simply continues to the next line and serves the smoothie. Nothing forced the programmer to check the result. The compiler didn't complain. The runtime didn't complain. The warning was simply ignored. That's why ordinary return values are sometimes called ignorable. The language doesn't force anyone to pay attention to them. So you might be thinking, well, that's easy. Just add an if statement, right? And yes, for a tiny program, that's exactly what we would do. After every function call, we would write something like, if the result is false, stop immediately. Problem solved. Or is it? Think about a much larger application. Maybe hundreds of functions call each other. Every single one now has to receive the error. Check it, then return it again. Every single layer becomes responsible for forwarding the error upward. That creates a lot of repetitive code. Even worse, if just one programmer forgets one if statement somewhere deep inside the application, the entire chain silently breaks again. So the idea works, it just doesn't scale very well. So, real world software isn't built from three layers. It might have dozens. Imagine our smoothie machine, just like before. The customer interacts with the screen, that talks to the cash register, which talks to the order queue, which talks to the blender controller, which talks to the ingredient dispenser, which finally communicates with the hardware sensors. Now imagine a hardware sensor detecting a rotten fruit. How does that information travel all the way back to the customer interface? Every intermediate function must remember to check the result, then return it again. Then the next function repeats exactly the same process. That's a fragile design. One forgotten check anywhere in the chain, and the error disappears, the information disappears. Large software systems cannot rely on everyone remembering every single return value. So, this is exactly where exceptions become useful. Instead of quietly returning false, the function throws an exception. Think of it as pulling an emergency brake. Execution immediately stops at that point. The program doesn't politely ask every function to pass the message upward. Not anymore. Instead, the runtime automatically walks back through the call stack looking for the code that knows how to handle the problem. All those middle layers are skipped automatically. Nobody can accidentally forget to forward the error. Eventually, a suitable handler catches the exception and decides what to do. This is why exceptions exist. Not because programmers are careless, we are not blaming them, but because large software systems are simply too complicated to rely on every return value being checked perfectly. Now that we have seen the motivation, we can finally start talking about the C++ exception mechanism itself. We'll step away from the smoothie shop for a second and look at error handling in general. We'll discuss where errors come from, what kind of failures software has to deal with, and why designing good error handling is much harder than simply detecting that something went wrong. Once we understand those ideas, learning the actual C++ syntax for throw, try, or catch will feel much more natural. Error handling has always been one of the hardest parts of programming. Writing the code that performs the normal task is usually the easy part. The difficult part is deciding what should happen when that task fails. Suppose you are saving a file. Normally, you just write the data and you're done. But what if the disk was full? What if the user doesn't have permission? What if the file disappears halfway through? Suddenly, your program has several new execution paths. That makes the code harder to read and harder to maintain. Another challenge is cleanup. Maybe you have already opened a file or allocated some memory. If an error occurs, you need to release those resources before leaving. Otherwise, you create bugs like memory leaks or locked files and stuff like that. Sometimes you don't just want to stop. Sometimes you want to recover and continue. C++ exceptions were designed to help organize these situations instead of scattering error checks throughout the entire program. Now we will look at cause of errors. Here, not every error comes from bad programming. Some problems begin long before anyone writes a single line of code. Here, the first category is specification errors. These happen when someone asks the software to do something that it was never designed to do. Then we have design errors. Maybe the requirements were correct, but the software architecture forgot an important feature or handled it incorrectly. Next comes the programming error or simply bugs. These are mistakes we make while writing the code. Wrong conditions, incorrect calculations, forgotten edge cases, and many more. Finally, there are third-party libraries or third-party components. Modern software depends on libraries, frameworks, and operating systems. Even if your own code is perfect, an external component can still fail. The important lesson is this: not every error is under your control. Good software assumes that failures can come from many different places at many different times, but it prepares for them according to the plan. Now, as programmers, we can't fix mistakes that happen during the programmers meeting or the requirements meeting. We also can't rewrite an entire operating system just because it has some bug. Those problems are usually discovered during testing or, unfortunately, after the software has already been released. What we can do is prepare our own code for situations we expect might happen. So, for example, hardware can fail, files might not open, memory allocation might fail, users might provide invalid input. These are situations we can anticipate. Instead of pretending they'll never happen, we design our software so it knows how to respond. That's really the mindset behind exception handling. We're not expecting failure every time. We are simply making sure that if failure does happen, the program reacts in a controlled and predictable way. Now, let's start with hardware errors. These happen when the physical environment behaves differently from what our software expects. For example, imagine a faulty memory chip. A value stored in a memory could suddenly become corrupted. Or perhaps you are writing data to a disk. The disk might become full, as we have already discussed. It might even fail completely. Another possibility is that something goes wrong while the operating system is loading your program. These aren't mistakes in your C++ codes. They are problems in the environment your program depends on. Fortunately, operating systems often notify us about many hardware-related problems, so our software can then react appropriately. Of course, not every hardware failure can be detected. Operating system itself is another software, so some are simply too rare or too unpredictable for us to handle properly. That raises an interesting question. Which hardware failures should we prepare for then? The honest answer is, well, not all of them. Trying to handle every possible hardware problem would make the software incredibly complicated. Instead, programmers usually make a practical compromise. If the operating system reports an error, we respond to it. If a very rare hardware failure occurs with no warning, we often accept that there's little we can reasonably do. This idea comes up a lot in software engineering, to be honest. Perfect software doesn't exist. Instead, we balance complexity against likelihood. We spend our effort handling failures that are realistic and important, rather than trying to prepare for every single imaginable possibilities and scenarios out there. Now, let's talk about software errors. Software errors can be divided into two broad categories. The first is external errors. These happen because someone asks our program to do something invalid. Maybe a function receives an illegal parameter. Maybe an input file has the wrong format. Or maybe the user performs a sequence of actions that simply doesn't make any sense in the eyes of the program. So, after this external category, we have internal errors. These happen inside the implementation itself. For example, the program might run out of memory, or an algorithm might encounter an extreme case that it wasn't designed to handle efficiently. Notice the difference. External errors come from outside the program, and internal errors happen inside the program while it's working. Both kinds of errors are important, and both may eventually result in an exception being thrown. Now, detecting an error is often the easy part. Modern operating systems, programming languages, and libraries, they are actually quite good at telling us when something has gone wrong. The harder question is this: what should the program do next? Suppose you detect that a file couldn't be opened. Should you ask the user to choose another file? Or should you create a new one? Or should you retry automatically? Or should you stop the program? There isn't always one correct answer. Designing very good recovery strategies is usually much harder than writing the code that detects the problem in the first place. That's why error handling deserves careful thought. It's part of the software design, it's not a part of the implementation itself. So, here comes our defensive programming mechanism. It's a style, so a useful way to think about programming is to compare it with defensive driving. Even if you're following every traffic rule perfectly, you still watch what other drivers are doing. You don't assume everyone else will behave correctly. Programming is very similar to that. Even if your own code is correct, files can be corrupted, users can make mistakes, networks can disconnect, libraries can fail, and many more things can happen. Defensive programming means writing software that expects unexpected situations. That doesn't mean filling every function with endless checks. It means thinking ahead. If something goes wrong here, what should happen? Can I detect it early? Or can I recover from it? Sometimes good defensive programming means that the user never even notices that a problem has occurred. That's usually the best outcome. Now, Once an error has been detected, we have several possible responses. There isn't one universal solution. Sometimes a component is capable of fixing the program entirely by itself. That's great because the rest of the application never needs to know that anything actually happened. But other times, the component itself can't solve the problem. So in that case, it simply reports the error to a higher level of the program. That higher level may have more context and be able to make a better decision than the lower level. The idea is important when working with exception. Not every function should try to recover. Sometimes its responsibility is to simply detect the problem, then clean up resources, and let someone else handle the rest. One possible response is the simplest one: terminate the program immediately. This is called aborting execution. It's certainly effective, the program stops, nothing else can go wrong. Okay? But it's also the least helpful option. The user may lose their work, no useful error message may be displayed, nothing may be written to a log file, and the next time the program crashes, nobody knows why. Many systems, unfortunately, behave this way by default when an exception isn't handled. As programmers, we usually try to avoid situations like this, but a controlled failure is almost always better than an unexplained crash. Now, let's talk about a much better approach, which is controlled termination. The program still ends, but before it does, it cleans up after itself. Files are closed, memory is released, error information is written to a log, the user receives a meaningful message explaining what exactly happened. Only then the program exits. This makes debugging much easier, and it also provides a much better experience for the user. Even though the operation failed, the software behaved professionally instead of simply disappearing. Now, sometimes the best response is to do nothing. That sounds strange at first, but not every error is equally important. It's a bit sneaky, but we'll still talk about it. Suppose a program briefly loses the mouse position. Maybe the cursor jumps slightly. That's annoying, but it doesn't prevent the software from doing its main job. In situations like that, ignoring the problem may actually be the correct design choice. Of course, this approach should be used carefully. Ignoring important errors usually creates bigger problems later, so you should keep that in mind while doing something like this. But for very small, non-critical issues, continuing execution can be perfectly responsible and reasonable. Another strategy is to undo the operation entirely. Think of it like a transaction at the bank. Either everything succeeds or nothing changes at all. Suppose you are updating a large data structure. Instead of modifying the original immediately, you first make a copy. You apply all your changes to that exact copy. If everything succeeds, you replace the original with the new version. If an error occurs, you simply discard the copy. You might try again or you might not, but you didn't touch the original data. The original data remains intact, and this gives the program a very predictable state after the failure. The downside is cost, of course, since you will have to make the copy of the original data structure. So this thing takes both memory and time. So while rollback sounds very attractive, it isn't always practical. Another possibility is recovery. Imagine a function detects an error but doesn't know how to fix it. Instead of stopping the entire application, it first cleans up any resources it owns. Then it reports the problem to a higher level of the program. That higher level might know what to do, and maybe it asks the user for another file. Maybe it retries the operation, or maybe it switches to a backup resource. This is one of the biggest strengths of exceptions. Lower level code doesn't have to know the entire recovery process. It only has to report the problem cleanly. Now, the final strategy is to actually correct the error and try again. Sometimes that's easy. For example, if a network packet gets lost, sending it again might solve the problem. Unfortunately, many failures aren't that simple. If the computer has run out of memory, repeating exactly the same operation probably won't help. Somebody or something has to change the situation first. That's why automatic recovery is often the hardest part of error handling. Detecting the problem is easy. Fixing it reliably is much more challenging. Now let's think of a classic example that we have been talking about. What happens when the program runs out of memory? Detecting the problem is straightforward. Recovering from it is much harder. If allocating memory already failed, your recovery code shouldn't try to allocate even more memory. One possible technique is to reserve a small block of memory when the program starts. You don't use it during normal execution, it's simply kept aside. If an out of memory condition occurs, you immediately release that reserved memory. Now you have enough space to log the error, display a message, or perform some final cleanup before shutting down. It's a clever trick and it shows an important principle. Good error handling often requires planning long before the error even happens. So far, we've talked about why exceptions exist. Now, let's start looking at how C++ actually represents them. In C++, an exception isn't just a message. It isn't simply an integer error code either. An exception is an object. That means we can organize different kinds of errors into class hierarchies just like any other object-oriented design. For example, one group of exceptions might describe file errors, another might represent arithmetic errors, another might deal with memory allocations. The C++ standard library already provides many useful exception classes like this, and you can even also create your own classes. In most situations, though, it's better to extend the existing standard hierarchy instead of inventing a completely unrelated one. That way, your code behaves consistently with the C++ ecosystem. And the nice thing is that once you understand inheritance, exception hierarchies feel very natural. They're simply another application of object-oriented programming. And one of the biggest advantages of hierarchy is flexibility. Imagine your program performs many different mathematical operations. Perhaps one function can detect an overflow, and another might detect division by zero. So, some parts of the program may know exactly how to recover from an overflow, and those functions can catch only that specific exception, while other parts of the application may not care about that exact reason. They simply know that some arithmetic operation failed, and those parts can catch a more general base class instead. So, this lets different layers of your application work at different levels of abstraction. And remember that these exception types are just ordinary C++ classes. You define constructors, you inherit from base classes, you can even add member functions if your application needs additional information about the error or according to your error handling pattern that you have designed already. Now, let's talk about exception specification. A function could declare which exception types it was allowed to let escape. So what I'm trying to say is here you can see we have a void function here, and then we are throwing from an already existing exception list, let's say. Or we can also have an empty throw like this. This empty version is a promise that the function would never let any exception escape. If that promise was broken, the program terminates immediately. So that sounds useful, but unfortunately in practice, these exception specifications caused more problem than they solved. They were eventually removed from modern C++. So if you encounter them in older code, it's useful to recognize the syntax, but for new code, you generally won't write exception specifications like these anymore. Now, let's look at what actually happens when an exception is thrown. Suppose a function detects an error. Instead of returning a value, it creates an exception object and uses the throw keyword. The moment that happens, normal execution stops immediately. The function doesn't continue, the caller doesn't continue either. Instead, the runtime starts searching for someone willing to handle that exception. It moves upward through the call stack, and this process of moving towards the call stack is called stack unwinding. Eventually, it either finds a matching catch block or reaches the top of the program. If nobody catches the exception, the program just simply terminates. This automatic search is what makes exception so powerful. You don't have to manually pass error information through every intermediate function. The runtime does that work exactly for you. Let's talk about exception handlers now. A catch block is called an exception handler. Every handler belongs to a try block. Only exceptions thrown inside that try block can be caught by its associated handlers. Another detail that's easy to overlook is that exception objects are copied during exception handling. So that's one reason exception classes should have a proper copy constructor. So here, suppose we are calculating an average. Most of the time that's straightforward, but there are two obvious failure cases. First, the number of values might be 0. Dividing by 0 isn't allowed. And second, the total sum might overflow. Instead of pretending these situations can't happen, we can represent them as different exception types. Then each one can be handled appropriately. Here's another benefit of inheritance. Suppose you have several related exception classes. Instead of writing a catch block for every single derived type, you can catch their common base class. Usually, you will catch it by reference. That's important. Catching by reference avoids unnecessary copying. It also preserves polymorphism. If you catch by value, object slicing can occur. The derived part of the object may be lost. So the common style in C++ looks like this. Here's catch, const, standard, then an exception, and here's the reference that we have been talking about. That's how you introduce reference, and then the object. That one handler can process many different exception types derived from standard exception. It's both simpler and more flexible than writing dozens of separate different classes. So let's go back to our average example. Suppose we only handled 3 specific exception types. That seems fine until something unexpected happens. Maybe the program runs out of memory, the standard library throws a standard bad allocation, but our code never catches it. So now what? The exception keeps moving upward through the call stack, and if nobody handles it, the runtime eventually gives up and terminates the program. That's why it's important to think carefully about which exceptions your program might encounter. Not just the ones you expect, also the ones that can be thrown indirectly by libraries or language features you use. Sometimes you simply want to make sure nothing escapes at all. C++ provides a special catch-all handler. It looks like this. Yeah, literally 3 dots. And it means that catch any exception. This is extremely useful near the very top of an application. For example, inside the main function. So if an unexpected exception reaches that point, you can log the error, display a friendly message, and exit cleanly instead of crashing without explanation. Notice that I said near the top. Catch-all handlers usually shouldn't appear deep inside your program. Otherwise, they may intercept exceptions that another part of the application could have handled much more intelligently. So use them carefully. They are, of course, a safety net, but not your first choice. And here, one of the nicest features of C++ exceptions is that try blocks can be nested. Imagine a large function. Most of it might have one general error handler. But inside that function, one small section performs a risky calculation. You can wrap just that part in its own try block. If the local handler understands the problem, it can fix it immediately. If not, It simply lets the exception continue outward. The outer handler still has a chance to respond. This lets different parts of the program take responsibility for different kinds of problem. It's a clean way to separate local recovery from an application-wide recovery. So, think of nested try blocks as different levels of responsibility. The innermost code knows the most about the operation when it's performing, so it should handle problems that only it understands. The outer layers knows less the outer layers know less about the implementation, but they understand the application's overall behavior, so they make broader decisions. Now, let's get one step further and discuss exception safety. We will see how to write classes that remain correct even when exceptions occur in the middle of an operation. What happens inside our classes when an exception occurs? Imagine you are halfway through modifying an object, you've already changed two member variables, then an exception is thrown before you finish. What state is the object in right now? Can it still be used? Can it at least be destroyed safely? These questions fall under a topic called exception safety. Writing exception-safe code isn't easy. In object-oriented programming, much of the implementation is hidden behind class interfaces. As users of a class, we often don't know exactly what happens inside a member function. Inheritance adds another challenge. A base class pointer might actually refer to many different derived types. Each one may behave differently during failures. Because of all this, exception safety isn't just about catching exceptions anymore. It's about guaranteeing that objects remain well behaved when exceptions occur. To make exceptions safely manageable, programmers usually define a clear contract. The contract tells users what they can expect if an operation fails. Instead of every class inventing its own rules, we group guarantees into a few well-known categories. You will see 4 of them on this slide. Here we are talking about the base guarantee, the strong guarantee, the no-throw guarantee, and exception neutrality. Think of these as different levels of promise. Some promise that the object remains usable. Others promise that absolutely nothing changes if an error occurs. The stronger the guarantee, the easier life becomes for the person using the class. But stronger guarantees are also harder to implement. Let's look at each one individually. We will start with the weakest guarantee. It's the basic guarantee. Suppose an operation throws an exception. The object doesn't have to stay exactly the same. Some member variables may already have changed. That's acceptable. But two important promises remain. First, the object must not leak resources. Second, it must remain in a valid state. Maybe the data changed. Maybe the operation only completed halfway. That's okay as long as they're destroying the object completely safely. Think of it this way, that the object may be different, but it must never become broken. That minimum promise is enough for many different classes. It's also much easier to implement than the stronger guarantees that we will discuss next. The strong guarantee goes much further. Here, the operation behaves almost like a database transaction. Either everything succeeds or nothing changes. Suppose you are modifying a container. If an exception occurs halfway through, the object is restored to exactly the state it had before the operation even started. From the caller's perspective, it's as though the operation never happened. That's a wonderful guarantee if you ask me. Users of the class don't need to worry about partial updates. One common implementation technique is the copy and swap. So here you make a copy, you modify the copy, and then you replace the original only after everything succeeds. Of course, copying large objects costs both memory and execution time. So, although the strong guarantee is attractive, it isn't always the most practical choice. Next, we reach the strongest promise of all, the no-throw guarantee. This guarantee says something very simple. This operation will never let an exception escape. From the caller's point of view, that's perfectly ideal. There's no need to surround the call with a try block. The operation is guaranteed not to fail through exceptions. Of course, making that promise is extremely difficult. Complex operations often depend on memory allocation, file access, or other functions that can themselves throw exceptions. So this guarantee is usually reserved for operations that truly can be made safe. A good example is many destructors. We will come back to those in a few minutes, but the important point is the stronger the promise, the harder it is for the class developer to keep that promise. Now, the final guarantee has a different purpose. It's called exception neutrality. Imagine your class calls another library. That library throws an exception. Your class doesn't actually know how to fix that problem. So, what should it do? Usually, it performs any local cleanup it needs, then it simply throws the same exception again. It doesn't replace it, it doesn't hide it, it allows the original exception to continue upward unchanged. This is what's called propagating the exception. Exception neutral code doesn't pretend to solve problems it doesn't understand. Instead, it lets higher level code make the final decision. You'll see this pattern very often in well-designed libraries. Constructors have one very special rule. An object officially exists only after its constructor finishes successfully. If an exception is thrown before the constructor completes, the object never comes into existence. That's an important idea. From C++'s point of view, construction failed completely. The good news is that C++ automatically cleans up member objects and base classes that were already constructed. Their destructors run automatically during stack unwinding. However, this automatic cleanup has one important limitation. It applies only to objects that C++ already knows about. As we'll see on the next slide, raw dynamically allocated memory is a different story. Suppose your class contains a raw pointer. You allocate the memory using new, the new keyword. If construction later fails, that dynamically allocated memory isn't automatically deleted for you. That's one reason raw pointers require extra care. So initialize the pointer to null pointer in the initializer list, then perform the actual allocation inside the constructor body. Why? Because once execution enters the constructor body, you can use normal exception handling if something goes wrong. If allocation fails, the pointer is still safely set to null pointer. Your object is left in a much safer state. Today, we would usually solve this problem with smart pointers, but understanding why raw pointers are dangerous helps explain why smart pointers became so popular. We will talk about that in the later lectures. So here, let's say suppose construction fails. Can we somehow recover and continue using that object? The answer is no. The object never finished construction, so there is no object to continue using. C++ automatically destroys every fully constructed member object. That's good. But sometimes we still want to react to the failure. Maybe we want to log what happened. Maybe we want to record diagnostic information or other kind of logs. C++ provides a feature specially for this situation. It's called a function try block. Unlike an ordinary try block, it can catch exceptions that occur during member function initialization or base class construction. Let's see what that looks like. Normally, a constructor body begins only after every member has already been initialized. That means a regular try block inside the constructor body is already too late to catch initialization failures. A function try block solves that problem. The try keyword appears before the constructor itself. Its catch blocks come after the constructor body. One important detail to remember is by the time execution reaches the catch block, stack unwinding has already happened. Every successfully constructed member has already been destroyed. So the catch block is usually used for logging, reporting, or translating the exception rather than trying to continue construction. So let's see a small example. Here we will create our example1.cpp. We will include IO stream. Then let's include standard except. Let's define a class database. Public, our constructor is database, where we will simulate that the connection actually failed. So now we have our application. In the application, our application owns a database, DB. And now here's the important syntax. We will write application try database. The try appears before the initializer list. When we write that our application started successfully, it will never run because the database already throws an exception. So let's catch it. Here we will catch it using the reference, and then we will standard C out. The application has thrown an error, and here we will end line and close the block. And here's our missing semicolon. Now in the main function, let's try to instantiate the app inside the try block and catch any kind of exception from here, and then let's standard C out that object construction failed or something like that. So now let's run it. See, it didn't even go through here. It just said error during application initialization, failed to connect to database. Here we asked what kind of error was that, and we placed that here, which was failed to connect the database, which is thrown from here and caught here. And then the object construction failed because we tried to catch all kind of exception that has been thrown inside from the try block here. So the program didn't continue with a half-built object. It cleanly failed. Now let's get back to our slides. Let's finish with one of the most important rules in modern C++. Never allow an exception to escape from a destructor. So imagine an exception is already being processed. The runtime starts unwinding the stack. As it moves backward, destructors are called automatically. Now suppose one of those destructors throws another exception. The runtime now has two active exceptions at the same time. It has no safe way to resolve that conflict. The result is immediate program termination through standard terminate. That's why destructors are expected to clean up resources quietly. If something goes wrong during cleanup, handle it inside the destructor itself. Don't throw it outside. Log it if necessary, but don't let another exception escape. Destructors should never throw exceptions. So, thank you for watching. I hope we learned something together today, and see you in the next lecture. Bye-bye.